Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, I speak with Ksenia Konyushkova, a Ph.D. student in the CVLab at Ecole Polytechnique Federale de Lausanne in Switzerland. Ksenia and I connected at NIPS back in December to discuss her very interesting research into some ways we might apply machine learning to ease the challenge of creating labeled datasets for machine learning. The first paper we discuss is Learning Active Learning from Data, which suggests a data-driven approach to active learning that trains a secondary model to identify unlabeled data points, which, when labeled, would likely have the greatest impact on our primary model's performance. We also discuss our paper, Learning Intelligent Dialogs for Bounding Box Annotation, in which she trains an agent to guide the actions of a human annotator to more quickly produce bounding boxes. Last week, I attended an investor conference in San Francisco. Having spent a couple of packed days being peppered with questions about the state of the AI market and its various players, I wrote about some of the key themes that emerged for the latest issue of my newsletter. If you're interested in the commercial side of the AI industry, you'll definitely want to check it out. If you don't already subscribe to my newsletter, visit twimlai.com/newsletter or just email info@twimlai.com asking to be added. You'll automatically get the latest issue when you sign up. Quickly, a bit about the next TWiML online meetup. On Tuesday, March 13th, Sean Devlin will be doing an in-depth review of reinforcement learning and presenting the Google DeepMind paper, Playing Atari with Deep Reinforcement Learning. Head over to twimlai.com/meetup to learn more or register. All right, let's roll. All right, everyone. We are here at NIPS, and I am with Ksenia Konyushkova. Ksenia is a Ph.D. student in the Computer Vision Lab at EPFL in Lausanne, Switzerland. Ksenia, welcome to the podcast.
Thank you. Nice to meet you today.
Absolutely. Great to meet you as well. So why don't we get started by having you tell us a little bit about your background and how you got involved in computer vision and machine learning, artificial intelligence?
Okay, so it probably all started with my master's degree when I just heard this cool name, machine learning.
Okay.
And I had very little idea what it is all about, but it sounded exciting. And then I learned that you can actually recognize cats in the pictures if you use machine learning. And then I thought, great, that's a thing for me. No, I'm
cat
kidding.
Recognition.
No, it wasn't the real motivation, but yeah, it just sounds fun. But yeah, it sounded like a fun field to be, and it was probably a little bit before it became so popular and so famous, but I was lucky to be there at the beginning. So I joined the program in machine learning and algorithms in the University of Helsinki, and after that I went for my Ph.D. program in Switzerland at Ecole Polytechnique Federale de Lausanne, and I joined the computer vision lab with Pascal Four, who is famous in the computer vision community. But as you know, today computer vision very much depends on machine learning, so it was a great match to combine these two fields that interest me.
Okay, awesome. And you're here at NIPS sharing some of the work you're doing, some of your research. Can you tell me a little bit about that?
Yes, sure. So I'm working in the field that is called active learning.
Okay.
So the basic idea is that normally in the traditional machine learning, we have a lot of training data which we collect from human experts, and then they provide us with the labels for this data when we're doing the supervised machine learning. And having this huge annotated corpus of data, we can train a model which will help us to predict for the new coming data what labels we assign. Either it's a classification or regression task. The problem that we're dealing with is that we don't have this training data available, and we're trying to select the data in the optimal way so that if we annotate it, we can learn the machine learning model as quickly as possible. So the idea is to reduce human annotation efforts and at the same time achieve a similar quality of performance of the machine learning algorithms. And what I'm doing, I'm presenting the work that is called Learning Active Learning from Data. So we're going even one step further, and instead of trying to construct some specific algorithm that would select data for us, we're trying to learn an algorithm from the previous examples of active learning algorithms runs. So, for example, the very popular active learning algorithm is called uncertainty sampling. In this case, we have, for example, suppose we have 10 data points that are labeled for us. It's very little, and we probably cannot predict much based on them. But we can still have a very rough idea of how the model should be. And then we can construct, for example, the decision hyperplane. And then we will select points that lie closest to the decision boundary. And we would think that as the model is the most uncertain right now about these points, if we annotate this kind of points, they would help to train a better model in the future. So instead of labeling the data just uniformly at random from the very big corpus, we select the data that would help the model the most. And this kind of algorithms, like I mentioned, uncertainty sampling, and there are many other ones that were introduced in the literature. The problem is that on different applications, they're all competing. Some of them are doing better in this scenario, some are doing better in that scenario. And for example, in my previous work, I worked on specific algorithm to work with images, so to take the advantage of the structure and some smoothness assumptions of the images to annotate data. But then there is nothing principled there, and we don't know which of the algorithm would actually perform the best a priori, so we have to test them, and this is all human annotation costs. So my idea is that we have some annotated data sets already, and then if we simulate the runs of this data collection process, we can actually see what kind of points led to a good behavior of active learning algorithm and which points didn't improve the quality much. And then we can try to predict in the future what kind of points should be selected. So in particular, I'm dealing with a situation where I just generate a lot of data myself, just like some synthetic data sets of very simple shapes, but they still have a lot of variability of them. In some cases, if I deal with binary classification, sometimes the classes overlap a lot, sometimes they're easily separable.
And they're two-dimensional shapes, or?
Yes, right now it's just very simple. We can do it with a very kind of cheap procedure with just two-dimensional data. And then we run active learning on them, just kind of this data collection. And then we look at the state of the classifier, how the classifier was trained, and the data points, and we look how much adding each kind of data point reduced the classification error for us. So, for example, we label 2 data points, we train a model, we look at what kind of error this model resulted in, as we know all the ground truth, as this is the simulated data. Then we try to select one more data point, and we get 3 points. Now on these 3 points, we can learn a new model, and it results in a new error. And now we can look at the difference between the error of the model with 2 points and error of the model with 3 points. And this difference would show us how much adding this third data point helped the model. And so now as we go on in training, we memorize the states of the classifier. For example, I'm dealing with something very simple like random forest classification. I can look at what was the depth of the tree, what was the variance of the forest, what was the cross-validated accuracy. And then we look at the data points. For example, what was the probability to belong to a certain class for a certain point. And we have how much in this situation, this particular data point reduced the error. So based on this data, after we collect it for all synthetic data sets, we can train a regressor that will predict in the future, based on the state of the classifier and given data points from the pool of unlabeled data, which of them would result in the highest reduction in error. And this is the sample that we select to be annotated. And we all started with this very simple two-dimensional data, and of course the easiest is to train it on the similar kind of data, and this is our simplest scenario. Then we try to complicate it more and more. For example, we deal with the Ksole-like problems when we have a kind of So we have a classification where the data is in the form of checkerboard. You can imagine, so we have like positive class, negative class, positive class, negative class, so they're kind of repeating in the checkerboard style.
Okay.
And this kind of data sets are more tricky for machine learning usually, and active learning is not an exception. And if we apply the very famous and very popular uncertainty sampling algorithm that is often difficult to outperform in normal situations, in this case it would perform even worse than random because it is confused by this checkerboard structure.
And is the difficulty with this structure because the regions are non-contiguous, or is it something else?
The thing is that, for example, if we imagine the checkerboard just 2 by 2, so we have, suppose we have red class on the top left, then blue class on the top right, and then blue class again on the bottom left and red class on the bottom right. Suppose that we selected one sample from the upper red class and one sample from the upper blue class as our initial examples. Then we construct some kind of decision boundary, and what uncertainty sampling would do, it would try to refine this boundary, and it would take a very long time to discover that there are 2 other regions of these classes that are in completely different order. So what uncertainty sampling is good at is it's at refining boundary when we already have some reasonable approximation of this boundary.
Okay.
And this can be a problem in many real data sets when one class can be represented by several modalities of examples.
Okay.
And so in this case, we show that then this very popular algorithm performs worse than just random sampling. By random sampling, I mean that we would just select data at random and then we label everything. So it's definitely not a very efficient strategy, but in this case, it does better than uncertainty sampling. However, if we learn the strategy from the previous examples of these active learning runs, it figures out that it shouldn't follow the strategy of refining the boundary. And for example, in this case, what it seems that it learns is that when the classifier is uncertain, it's better not to trust it at all, not to follow any of the predictions of the classifier, but instead just do some random exploration at the beginning until we collect enough data from which on which we can train a better classifier.
Okay.
And then we would be able to refine the boundary that would be more efficient.
And so this method doesn't involve trying to identify data points that are close to your decision boundary.
No, not anymore. Not anymore. Yeah, so it has the as a feature, as we have the regressor, it has some features as an input, and some of them are features of the classifier that just characterize how certain our classifier is, like how good is cross-validated accuracy, for example. And then some features, they characterize the data points, and one of the features could be the distance to the boundary, but it can also include some other features. For example, we can look at the distance to the other labeled points or distance to the unlabeled points. For example, it can characterize for us if the point is an outlier or if it lies in the dense region of the feature space.
Okay.
So it includes many more features, and including the distance to the boundary. But then if I study how much each of these features influences the decision of the regressor, the decision of which point to select by the active learning strategy, the distance to the boundary is not the first and most important criteria. It comes maybe like the fourth, and the first one was actually the certainty, the confidence of the classifier. So the strategy is adaptive as the active learning progresses and we collect more and more data, the classifier becomes more and more confident and the strategy adapts accordingly. And next we try to test this kind of algorithm that was learned from the data on the real data sets that are very different from these synthetic examples. In the synthetic examples, we just had this 2 by 2 two-dimensional features for the data points, but you cannot go very far with it, and probably it doesn't sound like a very exciting problem in machine learning. It definitely won't help us to classify cats. So next we move to the real data sets, and I'm I'm a part of Human Brain Project.
Okay.
That is a very big European project with a huge funding, trying to address the problem of understanding how human brain functions. And there are many, many researchers who work on it from very different perspectives. There are biologists, neuroscientists, there are physicists, and all kind of people. And so I'm also part of this project as trying to understand brain imaging.
Okay.
For example, we're dealing with electron microscopy scans of rat tissue, of rat brain tissue, and we're trying to segment some cellular structures in it. For example, we're on the cellular resolution and we can see the mitochondria, the synapses between neurons, we can identify membranes or other kinds of things. The other application in which I'm interested is having MRI scans of the brain and try to segment brain tumor of different types.
Okay.
And then I apply the same kind of strategy that I learned on the synthetic data to these real data sets of much higher dimensionality, much higher complexity. And also I have a very different data set, for example, for detecting credit card fraud transactions. So I have transactions from the bank for which we know that 99% of them are normal transactions, and then we have around 1% or even less of fraud transactions. And it's also a very laborious task to annotate this kind of data, because you need to annotate like thousands of data points before you start having only a dozen of examples of fraud. And this is only humans, they can do it. And the same goes, of course, for this biomedical imaging. Like, as a person who is not into biology or neuroscience, it is a very hard task to understand what is going on. And the time of these people is quite expensive, and we would better want them spend it on something more intelligent rather than annotating data for our algorithms. So these are the applications where active learning is the most interesting, in cases when only very specialized and educated humans can annotate data for us. And in this case, we also apply the same kind of strategy that we learned from synthetic data. And surprisingly, it works even in these cases. It can generalize to very different data sets. And how we understand it is that it learns a very general knowledge about active learning. For example, the rule such as when the classifier is uncertain, do random exploration, and when classifier is rather certain, refine the boundary. This should hold no matter how the data set looks like, and it would hold in the case of this simple two-dimensional data, in the case of very complex electron microscopy imaging data.
And so is the idea, when you take a step back and think about this in the context of a system like the imaging data, is the idea that how does this unfold in practice? Like, you have some minimal set of training data, and then you're envisioning that you would generate some other set of data and kind of send it out for annotation, or?
Okay, I see. So, in our example, for example, let's talk about this electron microscopy segmenting cellular structures. How we imagine it is that the user has a stack of tissue. So it's actually not a real image, it's a three-dimensional image. So it's kind of a cube, and in whatever direction we look at it, we can cut it in all directions, and we'll get the images of how the tissue looked like there. And so what we ask at the beginning, we ask the user to kind of take a brush in some program and indicate, here is like some part of mitochondria, and here is a part of background. And then based on this, our model would train some initial classifier, very, very, very rough one that would just like say, okay, mitochondria, for example, they're darker than background on average. So let's just use this as discriminative feature. It would train such a model, and then there will be some kind of grayish part in the tissue. And it would think, that classifier would think, I'm not sure what it belongs to. Does it belong to mitochondria, or does it belong to the background? And then the active learning would select this as some special part in the tissue which we want to be annotated, and then it brings the user to this part of the tissue and kind of highlights this area in which we would like to get more labels, and ask the user, please take a brush again and indicate whether this particular error is background or if this particular error is mitochondria. And then the user annotates again, and then the procedure iterates until we're satisfied with the results or until some budget of time is reached or something of the type.
And do you have that whole system running at this point end to end, or are you more modeling it from the data itself?
So right now I was mostly working just from the data.
Okay.
So we already have the labeled data and we simulate this active learning procedure, because in this case we can of course test many strategies. We can study how different parameters influence our algorithms. We can compare to many strategies. But we actually have students, a master student, who is working on putting it into a plugin that the neuroscientist would use. And I actually know some people who work in neuroscience, and I know one girl whose PhD topic is mostly at identifying mitochondria and trying to understand how they influence the neural diseases in the human brain. And what she does as a big part of her PhD work, she has to annotate this data manually. And I believe that she's very knowledgeable and she can do something more useful at that time if we can provide her with this plugin that only with 100 samples can provide the same quality of classification as with 10,000 samples, for example.
Wow.
So in some cases we can reduce the annotation effort very significantly.
So is that going from 10,000 required samples to 100, is that representative of the kind of results you've seen for different scenarios?
You mean across different applications?
Right.
Okay, it depends on the application how much active learning can actually improve our results.
Okay.
Yeah, so in some cases we can get a very dramatic decrease in the annotation time. In some cases it's not that much, but in any case we're reaching the same quality faster, and we can stop the procedure at any time when we reach the budget of time, and the classifier that we constructed at that point of time would be better than what we would construct if we just sample points at random. The other thing that we can look at is how human-friendly this kind of annotation environment is. For example, in my previous work, I worked particularly for images, and I tried to design a particular strategy for the 3D imaging stacks. And in this case, what we were saying is that it is very cumbersome if we have to annotate the stack just kind of pixel by pixel. Suppose that you are brought in some part of the stack and asked to annotate what is here, then you brought to some other place, you asked to annotate something then, some other and some other, and it can actually take quite a lot of time just because of this context switches, and you have to understand what is going on, and it's not so trivial to understand how these neurons connect with each other, for example. So one thing that we're looking at, we're trying to find some optimal cuts in this 3D plane. So we're just cutting them in various directions, and we're projecting data on this direction, on these planes, on these cuts, and we're trying to annotate some batches of samples instead of asking to annotate one by one, whatever the samples are. You can try to think of it
kind of like maximum uncertainty cuts or something.
In a sense, yeah. So we had some uncertainty measure that wasn't maybe not a standard one, but something special for the images. But then, we're trying to find a cut with a maximum uncertainty. And then there are other ways to work in this direction. So as I see it in active learning, there are these two components. One of them is we want to design an algorithm that would select the best possible sample. But on the other hand, we should still remember that there will be humans who annotate data for us. So we should make it as convenient and as easy for humans to label the data. And another thing that I've been working on also in this direction is getting labeled data for object detection. So the problem is very different. We just want to localize objects in images, the bottle, the TV screen, a human, these kind of things. And there are various, and for this we need bounding box annotation. So we need someone to draw a bounding box around every object, and from this we train. And there are various ways how we can collect it. We can ask the humans to draw it manually. This is the normal way of doing it. But on the other hand, we already have some kind of detectors that may be not as strong as we would like them to be, but we can already try to use the output of these detectors and show it to the users and ask the users to correct for the mistakes. And this is
are we talking about mistakes in terms of identifying the bounding boxes or labeling what's in the bounding boxes, or both?
Okay, so now I'm talking about identifying the location of the bounding box. Because in this scenario, we simplify the problem and we say that we already have image level annotations. So we already know that there is a bottle in this image, there is a door in this image, and now we want to know where this door is. So we split the problem in two separate ones, and we deal with the second one where we want to get the coordinates of these bounding boxes. And in this case, on the one hand, if we ask humans to draw an object, it is very fast. It is not very fast. It takes in the standard protocols, it might take up to 35 seconds to get one bounding box per image, and we need thousands of them for every class. So it results like in years and years of human work. And on the other hand, if we ask the users to verify the prediction of the classifier, it can be very fast. It takes like around 2 seconds, for example, just to say yes or no if it is a correct identification of the object. But it is not guaranteed to provide a bounding box that we would like to get. So if the user answers no, we have to repeat the procedure again, and we have to ask the user again where the box was. So what we're trying to do in this work, we're trying to balance between these two modalities of data annotation and trying to decide in what situations it's better to ask to draw a bounding box that is expensive but guaranteed to produce a label, and with which situations it's easier to verify the detector proposals, and it will result in a positively verified box quicker.
And is the methodology the same for this project as the one you previously described?
No, it's not exactly the same. But what unifies them is that we're still dealing with the problem of reducing human efforts, just approaching it from the other direction. So one direction is select what to annotate, and the other direction is select how to annotate. So what I believe is that both of them would be important, and if we just deal with one of them, we can get some good results on paper, on some simulations, but in practice, both of these directions would be important.
Interesting. I'm curious about how the system would go about directing the annotator to a specific area, meaning you have these data points that are annotated. What is it asking for? Is it asking for like some coordinate? Does it know like coordinates of uncertainty, or does it know something else? Okay,
so I didn't go into details of the protocol, but actually how we start, the task is to segment something, to segment mitochondria. And we started from over-segmenting images. So we use something that is called sleek superpixels or sleek supervoxels. So the idea is that it is unsupervised method that can provide segmentation of the image of the very fine grain that is not reflecting actually the boundaries of the object, but they're uniform, more or less. So we get like very small segments in the images that are all more or less uniform in their appearance, and every object would consist, for example, of 100 of such objects, of these supervoxels or superpixels. And then what the active learning algorithm identifies, it selects which supervoxel is the most uncertain.
And are the supervoxels, they're all uniform in shape and size?
More or less, yes. This is the property of the sleek supervoxels, is that more or less uniform and of a shape that is close to spherical or circular, depending if it's 3D or 2D stacks.
And so you can have multiple adjacent supervoxels that are the same value, essentially the same color, or...
Yes. So it's still, even if there is a very uniform part of the image, it would still try to divide it in some way so that they're still kept of more or less the same size and the same shape. It depends on the parameters how you specify. It's unsupervised algorithm, but you need to identify how compact you want them to be, how smooth you want them to be, this kind of things. But what we're trying to do is like to have them roughly circular small objects.
And are they overlapping?
No, they're not overlapping. So it is just kind of assignment of every pixel of the object to a super pixel. So they're called super pixels because they consist of multiple pixels, or super voxels, the same for voxels. And then what active learning does, it selects a super voxel or super pixel that needs to be annotated in this case. Or in case of this identifying the planes, it just identifies the area with several super voxels that are uncertain. So in this case, it would be just as if we have an image and then we highlight some kind of round area saying that we are interested in annotations there. And there we're also suggesting that if the objects are big enough, like mitochondria are rather big, and the selected area that we want the user to annotate is small, we can approximate it like just with 2 clicks of the mouse, just identifying the boundary of mitochondria if it is in the image. So it makes it even faster like this. So this is another example of working on this other direction of how convenient it is for user to annotate the data, combined together with the algorithm that selects what to annotate.
And so presumably if the user task is to then identify whether the boundary is in the image or in the voxel, super voxel, then you can kind of go from there to multiple super voxels with boundaries and determine which is where the mitochondria is. Is that what you're saying?
So how it looks like is that suppose we have a circle that overlaps the mitochondria a bit, but because mitochondria is rather big compared to the size of the circle, the boundary of mitochondria is more or less just a line. And we can ask the user to draw this line with 2 clicks and to identify on which side the mitochondria is. And then it would, we are able, from this line, we're able to go towards the assignment of supervoxels to particular classes. So when we have this
just
line,
that one assignment in this one supervoxel can tell you a whole, you can kind of project where the mitochondria is.
Exactly, So
Interesting. Well, this is really fascinating work. I appreciate you taking the time to share it with us. Where can folks learn more about your research? Do you have a website up on?
Yes, I have a website that is Ksenia.Konyushkova.com, and I try to keep it more or less updated about the recent research that I'm doing. For example, what I mentioned today, the work about bounding boxes, I just finished an internship last Friday at Google Research in Zurich, and this is a project that we were working on, and it's soon to be there, and before it is going to appear anywhere else.
Awesome. Well, thank you once again.
Thank you.
All right, everyone, that's our show for today. For more information on Ksenia or any of the topics covered in this episode, head on over to twimlai.com/talk/116. If you haven't already done so, make sure you head on over to iTunes as well to leave us your most gracious rating and review. It helps new listeners find us, which helps us grow. And of course, thanks so much for listening, and catch you next time.